I'll introduce Mark.
So Mark Avara is primarily interested in the dynamics of accretion disks around single and binary black holes and how to distinguish these from one another in time domain and multi-messenger data sets using observed variability of emitted light and outflows. Mark is also interested in the opportunities to accelerate astrophysical research and the studies of black hole accretion and MHD using machine learning and AI techniques. He obtained his bachelor's in physics at MIT and performed his graduate work at the University of Maryland in College Park using mag disks with Chris Reynolds and Jonathan McKinney. So, Mark, the floor is yours, and take it away whenever you are ready.
There we go.
Okay. You're in
Combination of 5 steps in a row to get everything to work together.
the So we cannot see anything on this.
It'll come up in a second. This guy.
Maybe if we connect and
Let me try that.
modulation.
Come back in a second.
So you put it on the speaker in presenter's mode that you had before.
Yeah.
If you want, even on my computer, you can use mine.
I think it's just frozen. Let me just plug this back in. See if that works.
Okay.
There we go.
Lovely.
Okay.
Okay.
All right.
Floor is yours.
All right. Sorry about that.
Maybe last thing, if you want to remove the bar, the control bar, you go to more. Yeah, more. On the right. Yeah, more.
That's right.
Hide the bar.
And
Hide video.
hide view.
I'm not sure is that, but try.
Yeah.
No.
Yeah, that's not it.
Okay. If you can just transport away.
It looks fine on Zoom, so.
Looks fine on Zoom.
Sure.
So
Okay.
if you want to move it up, further up, if you want.
I think it's not too much of an issue. I don't have much at the top anyways. Sorry about that. Yeah, thank you very much for the introduction, and it's a real pleasure to be back here. I had the pleasure of working with Belinda Wilkes before I started graduate school here a long time ago now, and I then switched towards theory from doing observational multi-messenger work on 3C objects, And I've slowly been creeping back in the direction of observations with applications to the HT and X-ray binaries. So it's a real pleasure to be back. And if you have any questions, feel free to interrupt, either raise your hand, or if you're in the balcony, maybe drop a flag or something like that so I notice them. So I'll be talking about simulations again of black hole accretion, just as we just saw, and there are a lot of similarities, so I won't go through too much of the same type of introductory material. Well, I'll be talking about highly magnetized disks, where the net vertical flux in the system that we would expect to accumulate, and if in the surrounding environment of a black hole, either an AGN or an X-ray binary, if there's enough magnetic flux to reach the mad state, we kind of expect that over some amount of time, either, the simulations show that net flux can be advected inwards or accreted inwards, especially along the surface flows. And then it should reach the mad state. But I want to stress that when we say mad disk, that means a couple of different things. It means that the horizon has reached this equilibrium state that is an upper limit of the amount of vertical flux that you can accumulate onto the horizon in balance with the accreting forces from the disk. And that sets the amount of flux when normalized by the accretion rate for the amount of flux on the horizon. But what about the rest of the disk? If you had just the right amount of vertical magnetic flux in the system, then you could be mad on the horizon. We would call that mad, but the disk might still be in the standard and normal evolution state, a sane disk. So I would say that always there's a second factor that you have to take into account, a parameter which I call the mad radius. And so when I talk about a mad disk, it'll mean at least it's mad on the horizon. And then there's a mad radius where the disk transitions in some way that I would say we don't fully understand from the part of the disk where the net vertical flux has been concentrated and is in balance with radial advective and accretion forces. And then outside of that, it's still sane. Maybe in X-ray binaries or maybe in AGN, the entire disk is mad. Maybe only the jet is mad. So for these simulations, putting mad aside for a moment, these are highly magnetized horizons that are tens of percents of the mad limit, but the rest of the disk is sane. And this is a bit higher magnetization than most simulations that people perform of sane disks, where they start with a weak net field. And so with a suite of simulations that I'll talk about today, we're exploring this intermediate regime. So, and by infinite, I mean not very large radial equilibrium, but not an infinite radial equilibrium. So ultimately, what we're trying to do is take a output from a GRMHD simulation, like we have a poloidal slice of the density in one of these systems on the left. This one happens to be mad. You can see this magnetic field flux tube that has erupted before it gets mixed back into the disk, and produce synthetic measurements for what the observations of the total light output, the bolometric luminosity as it varies in time, but also the spectral shape of these systems and what even an image might be like. And so for an X-ray binary, we're talking about X-ray variability, say, to probe what's happening near the horizon. And then in the case of AGN, that we can, luckily, now even image observations of what's happening in the near flow. But whenever you measure where most of the light is coming from, and that is pretty universally accepted to be in the high energy bands coming from very close to the horizon, I would say you're still sensitive to what's happening further out. So simulations that people do of these systems have a number of limitations. And for this, there was a very nice body of work, which was the Event Horizon Telescope Code Comparison Project, where they took the same setup, as similar as they could get, and run it on different computers with different codes and try to replicate it. And you can see, even with that, trying to replicate the problem exactly, there's a significant amount of variability in the mass accretion rate over tens of thousands of m, the unit of time we'll use, and significant variability in the normalized horizon scale flux as a function of time. Some of these are very low and then start to climb. Some of them are flat, etc. And then in even the profile of fundamental things that are really tied to, say, EHT observations, like the pressure or the temperature of the gas, there are significantly different profiles. And that's just on the physical side. You know, it's a problem because these simulations are very expensive to run in 3D GRMHD. You want to run them for several seconds, say, of equivalent of X-ray binary to try to trace out what might happen during, you know, one stage of an outburst. But, you know, getting to a week or a month time scale to do a full outburst is just beyond scope. So with these simulations, we run for as long as we can to talk about individual either transition states, transitions that happen really quickly in real systems, or we try to reach an equilibrium state that we think expresses one of the points on an outburst cycle, say for an X-ray burst. And then on the numerical side, there are a whole host of headaches that give me too much trouble to even talk about. So the problems that a really long and stable equilibrium state for a disk can address are quite important. So the general advantages is if you have a long simulation that has a very steady mass accretion rate, has an equilibrium in the disk out to a large radius. Remember, the longer you run the simulation, of course, the larger radius you reach in equilibrium to. The advantages of this is you can understand the variability, or you can characterize the variability of an accretion disk at low frequencies. And that's important because for X-ray binaries, in the X-ray emission, what we really are looking at a lot of the time is effectively low frequencies compared to the simulations. And then the radial equilibrium profile can reach a larger extent for a very long simulation. And you can also, with a very long and stable simulation, get better image sampling statistics, where you can pick and really see what the full range of images would look like. And that's really important for something like the Event Horizon Telescope, where you might take an image at a particular time where the horizon or the black hole is actually lensing a flare of emission from one particular piece of the disk. And that can change the entire profile. Now, luckily, those don't happen 50% of the time, but how long-lived those transients are, these are very important. And so long simulations that are in a stable state really allow us to characterize that, both for sane and mad disks. But it goes further. For a sane disk, if you have very long equilibrium state, you can start to study this global magnetic evolution. What I really mean by that is the mad transition radius, which can be at a large radius, as we would expect, given the amount of flux available in a real system. That radius can be pretty far out, 50 M, 100 M, maybe even 1,000 M. We won't be able to study the evolution of that radially if it fluctuates, if it's at 1,000 M, but we can do targeted runs where it's at between 10 and 50 M and look at the evolution of then the entirety of the mad region over the longest time scales for which advection diffusion processes affect the mad state. And then for the sane disk, I would argue, and I'd be curious if people ask or make comments at the end, if this is a picture that other people have as well, but I would argue for a sane disk, at least from a simulation standpoint, we don't really know what the equilibrium net horizon scale flux should be. Some simulations show it growing throughout the simulation. Some show that it kind of drops towards zero. It fluctuates with repeated bursts in some of them. In the simulations that I have, and will show it's quite stable over time, but that doesn't mean over realistic timescales that it wouldn't reach either an equilibrium state. In these units, the equilibrium state I would expect would either be mad or unity. And I would say in simulations that hasn't been shown either way. So how to address these? So a lot of the work that I've done is actually in the binary black hole context. And in binary black hole systems, you have the same problem. These are poloidal slices of accretion of a circumbinary disk around two equal mass supermassive black holes on circular orbits. And here the problem is that the evolution of the binary central cavity region and each individual mini-disk is sensitive to the qualitative structures in the circumbinary disk. But the separation in scale here is even worse, because the separation might be 50 M, and then the evolution timescale for this disk is extremely long compared to the equilibrium timescale for the inner regions of the mini disks. But if you don't run the circumbinary disk simulation long enough, you don't get the qualitative features right, like this overdense lump. This is density here. this overdense lump that orbits and actually dominates the variability of accretion rate onto each black hole. This has an eccentricity in the circumbinary disk that develops. And it was only in the last, I would say, 5-6 years that the circumbinary disk simulations have been run long enough to reach an equilibrium state in 3D MHD, which is different than 2D hydrodynamics. So you really have to go to 3D MHD. And then what we did in this case is we pre-evolved the circumbinary disk to try and get that right. And then with a multi-mesh code that I led the development of called Patchwork MHD, we then added a mesh and filled in the central region because the evolution timescales are much faster. So I'll do kind of a similar thing here for the single black hole, but I'll try to start with physical initial conditions that allow for the long evolution and stable evolution that I was talking about being necessary and motivating. But then also using a grid with Athena++, that's the code that I'll use for all of the simulations you see. Using a grid evolution that also enables running the problem for a faster and longer, more efficiently and for a longer period of time. So the initial conditions we use, they're not radically different than people have used in the past, but we get qualitatively different results, and they are improved, I think, in some specific ways. So for these simulations, we start with a Fishbone-Moncrieff hydroequilibrium torus. That equilibrium state, of course, only applies to the gas. But we start with a weak field, in this case, 2 alternating magnetic loops. Why 2? Because we're trying to reach a sane case where there's, where once we reach an equilibrium, we run these simulations long enough to reach an equilibrium over all of this initial disk period, or at least that's the goal. Then all of this net field should mix, and we should have a very stable net vertical flux on the horizon as a function of time. So that's the motivation for these. We start with the torus as large radially as we can, and the goal there is to basically only perform our analysis on what the disk state should be on regions that are filled in, and so are absolutely independent, or at least as close as we can get to the initial conditions of the torus. Yes. Yeah, so the question is, where is the inner edge of the torus? And here, the 2 fundamental Fishbone-Moncrieff parameters are, let's see if I can remember this, 23, and I think the pressure maximum is at near 40. Yeah, so these actually 37. And so those choices allow it to be not a huge torus. Often, if you want to run a very long simulation, what people do is they create a very large torus, which is great. It's a very large reservoir of material. But the problem then is that the outer portion, there's always a portion of the disk which is not in equilibrium yet. And non-equilibrium disks in their linear modes of the MRI create channel modes. And I worry, part of my motivation to do this is a worry that channel modes would then send significant flux and material into the inner disk and actually cause variability patterns that were larger than you would expect in a real disk. So here I start with a radially compact disk as far out as possible and run this until the entire disk is in equilibrium state. And though that reservoir is smaller, I can avoid transients that would be associated with larger disks. And these are non-cooling disks. They reach a hot ADAF-like state. And these are these sane but submad, but not, by a large degree submad simulations. So just in comparison to the EHT fiducial models in the code in the EHT library, where there are mad disks and sane disks, but a more traditional setup, because for the EHT library, they need to run a lot of simulations. Most of the simulations start with a torus that's further in for the sane disks, and starts further in, but is very large for the mad disks with a single loop. So I won't go into too many details about the comparison, but this is just to see the differences. So what do I do with the grid? So I want to run these for a really long time, hundreds of thousands of them, instead of the kind of most standard in the field, which is like 30, 40,000 M. And to do that, I use, these are different levels of refinement with Athena++. and I run for a long period of time so that the disk reaches an equilibrium where the horizon scale region is a bit under-resolved. And then I march in 3 stages. I march the highest refinement level towards the horizon. And so in the end, all of the disk of interest has a uniform refinement level in spherical polar coordinates. So let's see what the see what the simulations look like. So this is a movie of a poloidal slice of the density of as a function of time, the near horizon region with that funnel. And also in the equatorial plane, if I can skip ahead, this is a movie of an equatorial slice showing the density. There are also these spiral mode structures, which I encourage someone to ask me about in the question period. But we found was actually a bit of a headache, but also very interesting in these simulations. And because it's high horizon scale flux, a person who's run MAD simulations would say, oh, this is about to go mad. You see these low density regions where the magnetic field is pressing, choking the disk and starting to touch itself, where reconnection would happen, and then you would get a flux eruption, but the disk is not a MAD level here, so that doesn't happen. This is the final magnetic structure in these systems, so organized vertical flux that really creates a wide, well-defined funnel, and then the tangled field structure of a sane hot accretion flow. So just a quick word on inflow equilibrium. In this, I wanted to be able to claim that we had inflow equilibrium out to a large radius, competitive for the largest radii that people had done. But I would say there is an issue. Usually people use mass accretion rate being flat out to some radius as a proxy for where inflow-outflow equilibrium is obtained. But if you take a poloidal slice and you look at where one inflow timescale has occurred, 10 inflow timescales, 100, 1,000, 10,000, you'll see that it's different for the midplane where the radial velocity is lower. This is effectively just R over VR in a time phi average. It's different for the midplane than the wings, which are more highly magnetized and have a higher efficiency of accretion. And so something we've done, which I won't have time to talk about, is really look at the accretion flow as a function of azimuth. And this is just scaled out in there where you can see inflow equilibrium. That's masked a little bit in some of these. So going on, some of the measures. So we've run these simulations for over 200,000 M. I'll just point out that there are 3 simulations here. There's an EHT type compact torus. This is mass accretion rate as a function of time. And then in orange is our fiducial model, which reaches a phi value at about half the MAD level. And then the blue, at this point in time, I rescale the amount of horizon on the amount of vertical net flux threading the horizon I don't rescale it. Well, I would say I add alternate field of the alternate sign just in that region with the assumption that the reconnection time scale is at that radius is like the fastest time scale in the system, which is well motivated. And I reduce the horizon scale flux. And since all of the net vertical flux basically is on the horizon, I can do this process there. And then the blue simulation here is with a reduced phi value between 5 and 8. So it's a very interesting, I think, behavior that the mass accretion rate is effectively unchanged for long periods of time between these 2 simulations, nearly 100,000 M. They track each other very well. You'll notice this is just the expansion of the torus into filling in the inner region. And then this is the slow depletion of the reservoir of material. But we have a very long simulation with very high time frequency sampling of the fundamental characteristics, and we can really well characterize these simulations. This is the equivalent plot, but for the normalized phi parameter, you can see 30 is about half of the 60, which would be MAD for a thick disk, and then this lower value. You'll notice it seems very stable. Would over 10 times the length this reach the MAD state or drop down? I don't know. I think it's a very interesting question. So these are just radial profiles. I'll just fundamentally say that from radial profiles in azimuthal velocity, radial velocity, density, there are two main takeaways. One, for plus and minus 0.5 spin, which these two show, the density profile is very similar. And all of these profiles, especially the scale height Avara, is very sensitive, it is not as sensitive to the ISCO for the plus and minus spin as, plus and minus spin as you would expect. Having a large radial equilibrium, you actually see the effects of the inner physical boundary conditions starting from further out. So if you don't run a simulation for a long time, and if you only reach an inflow equilibrium state in the very inner 10M, you might actually have the wrong physical boundary conditions that you're reaching an equilibrium to. Yeah, okay. And the second takeaway that we found, I'll just summarize in words. We found that these simulations really support that accretion is in the disk a local process. So we find good agreement with shearing box simulations and the Reynolds to Maxwell stresses, and that helps give the reason for why these show such a self-similar ADAF type profile. Just one final takeaway from the analysis of these. Blue is our fiducial low magnetization simulation, and green is a more EHT type simulation, and this is the variability. And these are the kind of intermediate frequencies where you get most of the X-ray variability observations, and we see a significant difference. So I would say that reaching this equilibrium state allows us to characterize a variability profile that is less variable, at least in comparison to the EHT. That's well motivated and matches, but more work needs to be done. I'll skip this and I'll just leave with a few conclusions, which are, so I would say that we've matched our goals. We have long simulations, about 100,000 in time, which for a 10 solar mass black hole is about half a second. And we've been able to characterize a radial equilibrium profile like we wanted. And we're starting to see that by being very careful about how that's done, we see qualitatively different variability, more in line with what observations show. And the next step, and what I'm really excited about, is the implications for using this approach to study the variability of MAD systems, including the variability of all of the MAD region, including having equilibrium beyond the transition from the MAD inner disk to the outer disk. So I'll just leave it there. Thank you so much for your time.
Thanks, Mark, for the lovely talk. Any questions?
Hi, that was fascinating, Mark.
Thank you.
I just wanted to, I guess, make one comment for you and then have a question. The comment is that the power density spectrum that you showed was very much like what we see in the typical hard state for a black hole binary. So I don't know if you've compared to any data sets explicitly, but it really has that character.
Yeah, so I'll just say that there is a recent paper that came out that shows a transition state with flip-flops. And I like these flip-flops because they show a system that is rapidly changing between states at the timescales that we can simulate. And you're right, I think there is a pretty good agreement or an intriguing agreement between this and one of those states. Yeah.
Well, that's great. And then the question for you is really kind of a primary question about the setup of this, which is, in an X-ray binary system, you do have a natural source of magnetic field threading the disk, which is the presumably weak field of the companion star. And I don't know if that has any bearing, you think, on the long-term evolution of this towards something that's MAD or towards something that more MAD or more unity for the magnetization like you were describing.
Yeah, so I guess a question I would have, because I don't know, let's say, very much about stars, is whether or not you would expect a real net drift of the amount of large-scale flux that is made available to the central system. then I think it would be, which dominates the net flux variability that is available to accrete, or whatever is intrinsic to the disk. So a study that I've actually I haven't had time to do, but I think would make a good student project is to take this setup and look at the basically the correlation of flux from different radii, the net flux from different radii, and the horizon scale flux. And I looked at this for these simulations, and there is correlation out to the limit of my radial inflow equilibrium. I hypothesize that there is a radius, it's diminishing though. So I hypothesize that there is a radius at which beyond that, there is no significant correlation between the net vertical flux from MRI, natural dynamos in the disk and the horizon. I think one that is a very interesting radius because it sets the entire, everything inside of that integrated sets the entire variability profile of the net vertical flux on the horizon, maybe. But where that radius is, maybe it's beyond what we can simulate. So sorry, that's a long answer, but I think these are great questions, and maybe we can talk more offline.
Any other questions?
This may be a dumb question, but these magnetic field lines are threading the black hole. What's to prevent an observer inside the black hole from sending a message outside the black hole by modulating the bit of the magnetic field line that's inside the black hole?
Yeah, I would just say I am much more of an expert of what is outside the black hole, but and so I'll leave it to people studying non-GR or beyond Einsteinian gravity theories to maybe answer that question more fully. But I would just say that any my answer would be if there is any fluctuation of the field that you then try to twinge the field. I'm a violinist, so pluck the field and then have some signal follow that outwards, or inject a particle into the field at relative speeds that would go out. Those signals are still subject to the one-way flow of gravity at that point, or the overwhelming directionality of gravity, and so just no signal would be able to travel outwards along it.
Well, yeah, I imagine that happens. I just sort of don't understand how.
I'm not sure I would say I understand how either. Yeah.
I think it will be highly redshifted, so no signal can come to the observer outside.
Yeah.
It will be highly redshifted.
Yes.
So, because generally we think that it's the alpha wave which will translate the information, but I think none of the wave would reach to the observer far away because of the redshift, very close to the event horizon, it's infinite. So any signal from there it will trap. That is how I think it's like, and this is the membrane paradigm also. Everything is frozen outside there.
Well, thanks.
Any questions from the rafters? Student questions?
But I have a
Okay.
comment. If anyone want to ask?
They'll think about one and come up with one. Yeah.
So,
You can also ask after.
Yeah, that's true. Yeah.
I have again a comment and question.
Hmm.
So I also ran a multiple loop simulation like we did, but with multiple loops, not two. And also it was not a torus, rather different initial condition.
More like an infinite disk, yeah, or a self-similar
Yeah,
disk profile.
but not the magnetic field was not segmented. The outer disk is just only to supply the matter, not the magnetic field. Again, the same reason, because I didn't want to have the contribution from the outer disk as a magnetic field source.
Yeah.
And what we found that it forgets the initial condition at the end. It creates a large scale field, which is independent of the initial field geometry. And the MAT parameter saturates around 1 or 2 value. Now, my question would be, did you find the similar thing like the final field configuration? If you just take a snapshot of the toroidal field or colloidal field, azimuthally averaged, did you find that it is independent of the initial field geometry, or it still has the relics of the initial condition?
Yeah, so so once the field in the sane region of the disk, which is, let's say, basically all of the disk is tangled, then there's a split between the sign of the net vertical flux on the horizon and its closing field, which is a very large radii. So there's some outward advection, outward carry of the closing side of that loop. And some of it even passes beyond the edge of the domain in these simulations. But I would not say that that outer part is in inflow. I mean, it's outflowing, right? And it's not the limitation, which I've racked my brain at a way to try and get around, is that if we don't start with a very large disk, then we start with a cavity outside of that. Now, if we're comparing our simulations to something like a TDE, where the disk is thought to really be formed in a finite way, maybe that's good. But for something like an AGN, where you would expect maybe something like a quasi-self-similar profile going out several decades further in radius, how that would reach an equilibrium with the inner region, I'm not sure. I think, there's this kind of similar approach that people are starting to use, where they run cosmological, simulations and then zoom in and zoom in and zoom in. And initially, those required adding the field, which I didn't believe at all. And now there's starting to be more, similar, the magnetic field, but the resolution, I would argue, is maybe still not there to get the field evolution right, because those, predict wildly magnetized inner disks. And I think you can argue that that's just the time scale and the resolution. So I think we're pushing in the right direction, but computers are only so powerful. Hope that answers. We can talk more offline. Yeah.
Okay, so assuming that there are no more questions, we will ask like 2 quick questions. So the first one.
No, I'm just saying, get ready.
Oh, I'm start thinking about your questions. Is this transition mad radius that you talked about observation, like can we probe it observationally beyond the simulations? And second question, when you talked about the lump in the circumbinary case for the 2 supermassive black holes, and you mentioned that if you don't run the simulations for long enough, then you are not able to track consistently the effects of the lump or the circumbinary in the binary evolution. Do you expect that to have implications for the electromagnetic signal, or like the conclusions that you would get from predicting an electromagnetic signal from that lump if you don't run it long enough?
Good question. So for the first, there are papers arguing that this transition between the mad inner disk and the sane outer disk is the transition between the hot inner flow and the thin outer flow. And the argument being fundamentally that all of that extramagnetic field enhances the dissipation of energy and thermalization of the material, and that combined with the low density in that region causes it to be in the radiatively unstable state and puff up and create a hot flow. But the original argument that the transition from a thin to a thick inner disk, thin to a hot radiatively inefficient inner flow from just radiative arguments alone, those are strong arguments. So I don't see why there is not space for both a mad transition and a radiative transition. And I mean, somehow these must interplay with each other, but at least from my perspective, it's not one-to-one, and the mad transition is the transition from a thick to a thin disk in the highly sub-Eddington, but not yet high soft state in X-ray binaries, for instance. We can talk more offline about that, though. It's a good question. For the binary case, I think, so there has been a number of 3D GRMHD simulations now. We had the longest with that, but now there are competitor simulations with that with Athena++. The lump is a pretty for equal mass binary. It's a pretty like universal structure. It's seen in 2D viscous hydrodynamics. It's seen in 3D GRMHD, etc. The fundamental resolution requirements of it, I don't think have been met or proven. But its impact on the variability profile of the mass accretion rate on the two black holes is pretty universal. But then the contributions of it radiatively is maybe less widely like agreed upon. But whether the lump is there or not is still to some degree an open question. Noble 2012, they showed that if you add enough magnetization in the circumbinary disk, you can dissipate the lump. And then it comes back. So what is happening in the circumbinary disk over long time periods and its interaction with the large scale field in the system, it will come to bear on whether the lump is persistent, whether it's always there, whether it comes in and out, and all of that will be important for understanding binary variability. So, trying to, in the era of LSST, which we're going, this will be just my last comment, and something that I'll be working on at ISTA, where I'm transitioning to now, is, how do we separate AGN variability from binary supermassive black hole binary variability? The lump is key to this, as are other fundamental like accretion processes happening in the circumbinary disk. But the simulations are just so expensive for the binaries that without some 2D analogs, how do we do the type of libraries that really explore parameter space? So in the intro that you gave, you mentioned that I'm interested in AI and machine learning models. Real power from that, I think, will come in giving us good calibrated subgrid models from 3D GRMHD simulations for simplified hydrodynamic simulations, and then we can explore that parameter space and better understand the long timescale evolution of this circumbinary disk.
Great, thank you so much. So let's thank Mark again.
Thanks, Julian.
So